All right. Now that we have everything running, right? I got to start the recording and everything. Is there any questions from anybody?
No.
The thing we did last week, it was understandable. It was good.
With the calculator.
With the calculator? Awesome.
Yeah.
Awesome. You got it? Let me see what you got. Yeah. Winning now, you winning, right? Yes. Winning now, you winning now. All right, if there's no questions, if you don't burn so much time, let's start the lesson. All right. Once again, I really do apologize about the homework. Sorry about that. I messed up. Happy belated Halloween, everyone. I hope you all enjoyed Halloween this year.
Yeah,
There was a school party. I don't know if y'all went. I got you. Got you. Yeah. What else is coming up? We got pantry on Wednesday and Thursday. Make sure y'all go grab y'all groceries, get that bacon, get that chicken, Yo, real talk. You see, in 2 weeks when y'all have pantry, y'all better come stacked with stuff like carts, cars, yeah, like that one's gonna be crazy. I'm just letting y'all know, like crazy.
They did gift cards last
They
year.
did
Stop and Shop, $50 gift cards. Whoa.
on top of the turkey. Damn, damn. Nah, real talk. Like I remember seeing people walk out with 3-4 turkeys type of thing because people ain't coming type of nonsense. Like, yo, when y'all go, just Yeah, I know Popeyes got turkeys too. Ain't that crazy?
I heard about that last year.
Yeah,
I think so.
yeah. I don't know, but you got to go home and cook it yourself.
Yeah, some like Cajun style.
Yeah.
Right.
But I'm gonna diverge for a second. You know what the trick is though to the turkey though? Cut it up. Like don't cook the whole bird itself.
Yeah, you
That's
cut it
the
like
that's the trick.
like,
Yeah.
right.
No. I mean like like how you cook like chicken parts or whatever. Like you have the breast separate from the leg on. Like cut it up. That's the trick.
Well, most people like
But when you do that, like that's when it gets messed up. The breast meat is too dry, or like it's not cooked enough, and the leg meat is.
When it's turkey, I feel my so
Yeah.
like I sauce like
That's smart. Yeah,
like I do a big eating turkey.
that's fire.
Yeah, it's pretty.
That's fire. Yeah. I don't know, ideas. All right, so let's get into what we're talking to today, right? So we're gonna be doing sampling distributions. Yay! Mm-hmm. Mm-hmm. So we remember, right? A population can be thought of as a set of measurements or counts, right? Either existing or conceptually, right? I didn't write nothing, right?
Okay.
And then you remember that a sample is a subset of a population, right? It's like a piece of the population, right? So that's what we're going to distinguish a little bit again today, right? Even though we did it before. So when we compute a descriptive measure, such as an average, it makes a difference whether it was compounded from a population or from a sample. All right. So real quick, I want to introduce some old but new vocabulary. Excuse me. Thank you. Okay. So a statistic is a numerical descriptive measure of a sample. A parameter is a numerical descriptive measure of a population. Right? Remember this from like first day?
Yeah.
Right? So we're doing a little blast from the past today. Before I'm blocking you. See what I could do. Well, my bag is small. Let's do that. Okay. All right. So it is important to notice that for a given population, a specified parameter is a fixed quantity. On the other hand, the value of a statistic might vary depending on which sample has been selected, right? So parameters are fixed, samples can vary from sample to sample, right? So this is going to be kind of fun real quick. Right here. Oh, whoops, my fault. 1 second. All right, so we're going to look at some commonly used statistics and corresponding parameters. So, for example, when we have the mean, right? The statistic is X bar, but the parameter is mu, right? When we have the variance, the statistics is S squared, right? But the parameter is sigma squared, right? All on your formula sheet, by the way, right? For standard deviation, we have the statistic, which is S, right? But our parameter is sigma, right? For proportion, right, which is the probability of success for a binomial distribution, right? The statistic is p hat, right? And the parameter is rho, right? It looks like a p, but it's pronounced rho, right? So long story short, if you have English letters, right, you're talking about a statistic. If you have Greek letters, you're talking about parameters, right? All right. Oh, my fault. Yeah, my good side. All right. All right, so often we do not have access to all measurements of an entire population because of constraints such as time, money, or effort. So we must use measurements from a sample instead. In such cases, we will use a statistic such as X bar, this sample standard deviation, or p hat to make inferences about a corresponding population parameter, right? Mu, sigma, rho, for example. The principal types of inferences we will make are the following. All right. So just laying the groundwork for the rest of the class. So these are some types of inferences that we have. We have estimation, right? So in this type of inference, we estimate the value of a population parameter, right? That's coming up soon. We also have testing, right? In this type of inference, we formulate a decision about the value of a population parameter, right? And we have regression. In this type of inference, we make predictions or forecasts about the value, of a statistical variable, right? These are the money makers in statistics. In case y'all want to switch out majors, right?
Already.
No, it's mad simple. We've actually seen one of these already. We've already seen regression, right? Remember when we had the graph, right? And we did the scatter plot, and then we tried to figure out where is the graph going in the future, right? That's regression. That specifically, that's called linear regression, right? But there are other types of regression that exist as well, right? Unfortunately, we don't have enough time to go through all the other regressions, but just know that they exist. It's all the stuff that you remember from like high school that you were like, oh, what am I going to use this for? Like that's the regression stuff. You know? So anyway, to evaluate the reliability of our inferences, we will need to know the probability distribution for the statistics we are using. Such a probability distribution is called a sampling distribution, right? And then I'm going to show you guys an example. Before I do that, real quick. 2 seconds, real quick. Give y'all the definition of a sampling distribution. So a sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples of the same size from the same population. All right. So that's a sampling distribution. Let me give y'all an example real quick. It's gonna be fun real quick. Bless you, bless you. All right, so Pinedale, Wisconsin is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches must be returned to the pond. Only children under 12 years old may fish. And there's a limit of 5 fish. There's a limit of 5 fish may be kept per day. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. The pond contains only rainbow trout. Y'all ever tried that before? I don't know if that's good.
I never tried to eat it. I caught it.
You caught it before?
Actual fish?
Yeah.
Rainbow trout, yeah. They're really pretty.
I never seen one. I don't know.
Oh yeah.
I don't even know what it looks like.
Oh yeah, people fish with trout.
Yeah. Trout, but I never heard of rainbow trout.
Oh
yeah.
Rainbow trout.
Yeah. So it sounds tropical. So that's what I was wondering. Like y'all ever seen it before?
That's pretty native, pretty American.
It's from America.
Yeah, pretty American.
So only rainbow trout and has been well stocked for many years. Each child has no difficulty catching his or her limit of 5 trout. These are master fishes right here. Yeah. So as a project for her biometrics class, Susan kept a record of the lengths to the nearest inch of all the trout caught last summer. Hundreds of children visited the pond and caught their limit of 5 trout. So Susan has a lot of data. To make this table that I'm about to show you, Susan selected 100 children at random and listed the lengths of the 5 trout that they caught individually by a child in the sample. Then for each child, she listed the mean length of the 5 trout that child caught. Right. So each child caught 5 fish, right? She recorded their lengths and then she took an average of them, right? To produce a chart with the mean, right? I'm going to show you guys a piece of that chart because that chart is big, right? But just to give you an idea of what it looks like. So this is the chart that she produced right here.
That's huge.
Yeah. Obviously, though, remember from chapter 2, we have methods of simplifying the data so that we could understand it, right? But this is like the raw data right here, right? So for example, where it says sampled, all of these are children, right? Just random children, right? And then these are the trouts that they caught, like the different lengths of them. And when you add them all up and divide by how many is there, these are their means, right? So there's actually 100 of these, but this is just like the top portion of it.
Each child caught 5 fish, and that's like that, and then those means is the averages of like
those 5 that they caught individual. So there's many means here. Right? There's a means of means. I just made that up. I just made that up. All right, so now let's turn our attention to the following question. What is the average mean length of a trout taken from Pinedale Children's Pond last summer? right? Go ahead. Huh? No, but the average length though. Yeah, yeah. Yeah, not the number.
So you have to look for throw at the mean. Yeah.
Right.
You have to look
Right.
and
Well,
add them up.
Well, actually, what we do, you remember from chapter 2 when we had the frequency tables and stuff?
Yeah.
That's what we do.
Really?
Because that's a lot of work right there.
Yeah.
It's 100.
Yeah. Like that's
See which number pops up.
yeah. So here you go. This is what we're going to do, right? So we can get an idea of the average length by looking at the far right column of table 7, 8, whatever, right? But just looking at 100 of the X bar values doesn't tell us much. Let's organize them into a frequency table, right? And we use the class width of 0.38 to make the table, right? So here goes our table right here. Little blast from the past, right? Our frequency table, yay!
This size kind of really like see.
Got you.
Can
I pull it in?
Yeah, that's it.
All of them?
Yeah, one of them are on the block.
Damn. I don't know why they did that.
Here's an emergency.
Yeah. I don't know. You think they're powered maybe and the power went off on them? Let's see. They do something like that. It will just go scroll down after. So this is our frequency table, right? So we have our classes, right? We have our class limits, the lower and the upper, right? The frequency of how many times this length appeared, right? And then we have our relative frequency. This is all from the 100 numbers up here. Yeah, so what they are, right? This is looking at their means, right? Remember, there's like 100 numbers there, right? So we're producing a class limit, right? A frequency table, I meant to say, I'm sorry, where this is our lowest value, right? And then we add the class width to get to the next one, so on and so forth. Subtract one to get up here, etc. Right? And then, but the real magic that we have with this is this part, the relative frequency. All right. So show you what we're going to do with that. So techniques of section 2.1, right, dictate a class width of 0.4. However, this choice results to the nearest 10th class being beyond the data. Consequently, we shortened the class width slightly, right, and also stated that the first class with a value, right, slightly smaller than the smallest data value. The far right column of table 7.9 contains relative frequencies, right, f over 100. Recall that the relative frequency may be thought of as a probability, right? Now we're getting back to it. So we effectively have a probability distribution because X bar represents the mean length of a trout based on the sample of the 5 trouts caught by each child. We estimate the probability of X bar falling into each class by using the relative frequency, right? So the chance that a fish caught between 11.5 inches to 11.42 inches, right, is the relative frequency 0.05, right? For example. All right. The bars of the next figure, right, represent our estimated probabilities of X values based on the data of table 7.8. The bell-shaped curve represents the theoretical probability distribution that would be obtained if the number of children, i.e. the number of X bar values, were much larger. All right. So let me show you guys that real quick. So this is our bell-shaped curve right here, which we're getting from the data. All right. So on the y-axis right here, we have our relative frequency, right? Which goes from 0.05 to 0.30. On the, excuse me, on the x-axis, you have your class widths, right? And you notice that each one of these bars kind of forms a normal distribution, right? So that's what we're observing here. And this is all based on the 100 samples that we took from the fish, from the pond or whatever, right? All right, so this figure represents a probability sampling distribution for the sample mean X bar of the trout lengths based on random samples of size 5. We see that the distribution is mound shaped and even somewhat bell shaped, right? Irregularities are due to the small number of samples used, only 100 sample means, right? And the rather small sample size, 5 trout per child. These irregularities will become less obvious and even disappear. Let me get the rest of that for you. And even disappear, right? If the sample of children had been much larger. So if we used a larger number of classes in the figure, and if the number of trout in each sample became larger, right? In fact, the curve would eventually become a perfect bell-shaped curve. And we will discuss this property at some length in the next section when we talk about the central limit theorem. That's fire, you know? So what they're trying to say is if we increase our sample size large enough, right, any distribution becomes normal, right? And then we could do normal things to it, like change it to a z value, look it up in the chart, get an answer, right? This is fire, fire, fire. Mad cool stuff right here.
Stuff.
That's cool, I promise you, I promise you. So just so you know, there are other sampling distributions beside the X bar distribution, right? In the next section, we're going to be looking at sampling distributions for p hat, right? In the chapters ahead, we will see that other statistics have different sampling distributions. However, the X bar sampling distribution is very important, right? And it will serve us well in our inferential work for the next couple of chapters on estimating and testing, right? This is good stuff right here. So real quick, let's just rewind it back for a second. Let's just do a quick recap. So what does a sampling distribution tell us, right? So a sampling distribution gives us information regarding sample statistics such as X bar or P hat, right? The sampling distribution is based on values of the sample statistic from all samples of a specified size n, right? Sampling distributions are used to obtain information about corresponding population parameters. In the next sections and chapters, we will see how to obtain information about the value of the parameter mu from a sampling distribution of X bar, right? And we will also study, sorry about that. We will also study distributions of p hat, the sampling probability of success in the binomial trial. Awesome, awesome, awesome. Y'all gonna have to wait for next week to see that though. All right. Questions on this? Does it make sense?
So one of the homeworks for 7.1, we have to find the normal distribution. So they gave me like 3 sets of numbers. So
right.
What do I do first? Do I use the formula? Q equals the square root of NP and Q.
For not for 7.1, for 7, we use the Z formula.
The Z formula.
So Z equals X minus mu over sigma. You just plug in those numbers, you're gonna get a Z value. Then you just look it up in the chart, and then that's it. All right. Or use a calculator. You have options. All right. I like the calculator myself, I'll admit. All right.
It's gonna be in the test.
Yeah. Mhm. And then something else that we're gonna do next week, I'll be on the test also, and then y'all good to go after the week after. Mhm.
Oh, so 2 weeks. What's that?
2 weeks, yeah.
Oh.
What's it gonna be, the 16th?
Hmm?
The 16th?
That was gonna be
I don't even know what day today is. Hold on. Yeah, the 16th.
That's never tough.
Yeah.
Yeah.
2 weeks. Yeah. Now we got something else to learn next week.
So we,
Yeah.
test is gonna be about 4 topics? This
Um,
time? 'Cause we have learned, well,
Three, yeah. So we have the chapter 5, we have binomial distribution, and then we're gonna have normal distribution. And that's your whole test.
And what about what we learn next week?
One topic will be on it and one topic won't be. Just to fill up the class time, I had to go over a little bit. Yeah. But I know y'all wish that other topic we're gonna learn next week would be on it because it's so simple.
Yeah, yeah.
Just copy and paste. Yeah, just copy and paste. That's all it is. All right, so let's get into the fun stuff for today. The central limit theorem. Woo. Right? Oh, we about to dive in right now. This is like one of the coolest theorems ever. For real, for real. So the X-bar distribution, given that X is a normal distribution. So in the last section, we began a study of a distribution of X-bar values where X-bar was the sample mean length of 5 trout caught by the children in Pinedale's Children's Fishing Pond. Let's consider this example again in the light of a very important theorem of mathematical statistics. Yes, sir. It's about to be lit. Here comes the theorem. Here comes the theorem. Okay, ready? It's the bomb right here. So for a normal probability distribution, let X be a random variable with a normal distribution whose mean is mu and whose standard deviation is sigma, right? This is what we did before. Let X bar be the sample mean corresponding to the random sample of size n taken from the X distribution. Then the following is true. The X bar distribution is a normal distribution. We already know that, right? The mean of the X bar distribution is mu. That's new, right? And the standard deviation of the X bar distribution is sigma divided by the square root of n, right? So that's new right there. But still good though.
This is the one.
Yeah, it is. Unfortunately. All like one questions of it. All right, so we conclude from the theorem, right, that when X has a normal distribution, the X bar distribution will be normal for any sample size n, right? Furthermore, we can convert the X bar distribution to the standard normal Z distribution using the following formulas, right? So we about to get a whole formula to do everything. Oh, this about to be lit. Y'all even seen the formula before, but we just gonna refine it a little bit. Right? This is all on your formula sheet, by the way, right? So let's start from the top, right? So the mean for my X bar distribution is mu, right? This is all in chapter 7, by the way, if you're looking for it, right? The mean, the standard deviation for my X bar distribution is going to be the standard deviation divided by the square root of n, right? And then to convert it, we remember this formula here, Z is equal to X bar minus mu X bar over sigma X bar, but how it changes is it's going to become X bar minus mu over the standard deviation sigma divided by the square root of n, right? All of that is in chapter 7, right? You can look on your formula sheet and see that. N, remember, is my sample size. Mu is the mean of the X bar distribution. And sigma is the standard deviation of the X bar distribution, right? So when I say sigma here, I mean this sigma. Sigma divided by the square root of n, not sigma by itself. All right. Excuse me, sorry about that. This theorem, right, is a wonderful theorem. It states that the X bar distribution will be normal provided that the X bar distribution is normal. Excuse me, the X distribution, excuse me, is normal. The sample size n could be 2, 3, 4, or any other fixed sample size we wish. Furthermore, the mean of the X bar distribution is mu, same as for the X distribution, but the standard deviation is sigma divided by the square root of n, which is, of course, smaller than just the standard deviation sigma, right? And then in our next example, we're going to show that. All right. So check this out, check this out, check this out. It's going to be fun. So look at this, probability regarding X and X bar, right? Suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let X represent the length of a single trout taken at random from the pond. This group of biologists has determined that X has a normal distribution with mean mu is equal to 10.2 inches and a standard deviation of sigma is equal to 1.4 inches. All right. All right. So this is kind of like what last week was. This is last week right here, right? So here's this question, right? What is the probability that a single trout taken at random from the pond is between 8 and 12 inches long, all right? Just one single fish, right? So you remember how we did this, right? Quick little recap. Right, the X from the mean, right? And then we find our Z values and we look it up. Right, so we use the methods, right, where our mu is 10.2 and our standard deviation sigma is 1.4, right? We have our formula, Z is equal to X minus mu over sigma. We plug in the value for X minus the 10.2 divided by the 1.4. In this case, I want to know what is the probability of between 8 and 12, right? So 8 less than X less than 12. And we know that the probability is going to be what? We're switching it to the Z value now. 8 minus 10.2 over 1.4 less than Z less than 12 minus 10.2 over 1.4. Calculator. Calculator, right? And then we get the probability is going to be between, right? Negative 1.57 less than Z and less than 1.29. Calculator, look it up on a chart, whatever. Remember, this is your upper bound, lower bound, right? And then boom, you get 0.833, 0.8433, excuse me. All right? Simple stuff. We're kind of doing the same thing again today, but with a twist, right?
New words.
New words, yeah. So therefore, the probability is about 0.8433 that a single trout taken at random is between 8 and 12 inches long, right? So here comes our twist now. Because we already know how to do all that with the 100 numbers and everything, right? What we want to know is about the means, right? Remember, we took the mean for every child's fish, right? We took the mean for every child. Everybody got 5 fish and we took their means, right? So what is the probability that the mean length, X bar, of 5 trout taken at random is between 8 and 12. So you notice the difference there, right? Each child had got 5 fish, right? And we want to know, right, what is the probability that their mean length, right? Not the individual fish itself, the mean length of the 5 fish they caught, right, is going to be between 8 and 12. So that's the difference in the question right there. Oh, that was a crazy one, right? So if we let if we let the mean for the X bar distribution represent the mean of the distribution, then the theorem, right, will hold true. So we know that the mean for the X bar distribution is equal to the mean mu, which is 10.2, right? If sigma X bar, right, represents the standard deviation of the X bar distribution, then Parsi tells us that the standard deviation for the X bar distribution is equal to sigma divided by the square root of n. So what we're doing is we're going to take the standard deviation that we have and we're going to divide it by the square root of n, right? Or in this case, the square root of 5, the number of fish that each kid had, right? That's going to give us about 0.63, whatever, right? We create a standard z variable from the X bar, right? And we subtract it from the mean and divide by the standard deviation for the X bar distribution, right? We already know how to do this. It's going to be X bar minus 10.2 over the 0.63. And then let's look at what happens next. Good stuff, good stuff, good stuff. All right. So it's kind of the same thing, but the idea is a little different. So to standardize the interval, 8 less than X bar less than 12, we use 8 and then 12 in place of the X bar in the preceding formula. So we're just going to plug in the 8 right here. 8 minus the 10.2 divided by the 0.63. Remember, that's the standard deviation divided by the square root of n, right? Less than z less than 12 minus the 10.2 divided by the 0.63. We have new z values. We have a z value between negative 3.49 and 2.86, right? So the theorem tells us that the X bar has a normal distribution. Therefore, right, we look these up, right, or do it in the calculator, whatever, and then we're gonna get 0.9977. So the probability is about 0.9977 that the mean length based on a sample size of 5 is between 8 and 12, right? So that's what we're doing here. So looking at the results, right, from A and B, we see that the probabilities 0.8433 and 0.997 are quite different. And so why is this, right? So according to the theorem, right, the first theorem, right, both the X and the X bar have a normal distribution and both have the same mean of 10.2 inches. The difference is in the standard deviations for X and X bar. The standard deviation for the X distribution is sigma is equal to 1.4, but the standard deviation for the X bar distribution is sigma X bar is equal to sigma divided by the square root of n, right? So basically, right, if I know the whole population, right, I don't need to have I don't need to divide my standard deviation by how many numbers I have in there, right? But when I'm taking a sample, it becomes important, right? I have to divide it by the sample. So that's the idea here. So the standard deviation of the X bar distribution is less than half the standard deviation of the X distribution, right? So this figure is going to show us coming up. So when you look at the figure, we see that both curves use the same scale on the horizontal axis, right? The means are the same, and the shaded area above the interval from 8 to 12 in each group, it becomes clear that the smaller standard deviation of the X-bar distribution has the effect of gathering together much more. So let's take a look at that real quick. Let's take a look at that. So boom, these are the two distributions that we have here, right? So our first one is the X, right? This is our X distribution. That's a 0.8433. As you can see, it's still between the 8 and the 12. It's just that it's not as peaked, right? It's more spread out, right? Whereas when we take our X bar distribution right here, it becomes more peaked, less spread out, right? And we remember that standard deviation is a measure of error, right? So the higher the standard deviation, the more risk, the smaller, the less risks, right? So that's why this is. So theorem 7.1 describes the distribution of a particular statistic, namely the distribution of the sample means X bar, right? Whoops. Sorries about that. All right. So it describes the distribution of a particular statistic, namely the distribution of the sample mean X bar. The standard deviation of a statistic is referred to as the standard error of that statistic. All right. So now we get into new vocabulary, standard error. Let me just elaborate on that real quick. All right. So the standard error is a standard deviation of a sampling distribution for the X bar sampling distribution. So standard error is equal to sigma X bar, which is equal to sigma divided by the square root of n, right? That's called the standard error. All right, now that we know that, let's take this up a notch. Let's take this up a notch. So we're going to talk about the X bar distribution given that X follows any distribution, right? So the theorem, gives complete information about the X bar distribution provided the original X distribution is known to be normal. What happens if we don't have information about the shape of the original X distribution? The central limit theorem tells us what to expect, all right? So this is fire right here. So this is the real meat and potatoes behind the central limit theorem about to come up. Second part to it. So theorem 7.2. So the central limit theorem for any probability distribution, if X possesses any distribution with the mean mu and a standard deviation sigma, then the sample mean X bar based on a random sample of size n will have a distribution that approaches the distribution of a normal random variable with mean mu and standard deviation sigma divided by the square root of n as n increases without limit. So the central limit theorem is indeed surprising. It says that X can have any distribution whatsoever, but that as the sample size gets larger and larger, the distribution of X bar will approach a normal distribution. So from this relation, we begin to appreciate the scope and significance of the normal distribution, right? So as n increases, for whatever distribution, right, it becomes normal. And then once it's normal, we can do things with it, right? What's the probability of less than this or greater than that, right? This is good stuff right here, good stuff. Y'all gonna appreciate it at the 4-year school, I'm telling y'all. So in the central limit theorem, the degree to which the distribution of x bar values fits a normal distribution depends on both the selected value of n and the original distribution of x values. A natural question is, how large should the sample size be if we want to apply the central limit theorem, right? So after a great deal of theoretical as well as empirical study, statisticians agree that if n is 30 or larger, right? So if your sample size is of 30 or bigger, right? The x bar distribution will appear to be normal and the central limit theorem will apply. However, this rule should not be applied blindly. If the x distribution is definitely not symmetric about the mean, then the x bar distribution will also display a lack of symmetry. In such case, a sample size larger than 30 may be required to get a reasonable approximation to the normal, right? So in practice, it's a good idea when possible to make a histogram of sample x values. If the histogram is approximately mound shaped, right? And if it is more or less, hold up, let me get the rest of that. So more or less symmetric, right? Then we may be assured that for all practical purposes, the x bar distribution will be well approximated by a normal distribution, and the central limit theorem will apply when the sample size is 30 or larger. The main thing to remember is that in almost all practical applications, a sample size of 30 or more is adequate for the central limit theorem to hold. However, in a few rare applications, you may need a sample size larger than 30 to get reliable results, right? For example, right? Let's say you know someone that's studying nursing, right? And then they want to decide if like a medication is good for the population, right? They're not going to ask 30 people like, yo, what you thinking? And that's it, right? Right. They're going to ask like 10,000, right? So in medicine, right, your N has to be 10,000 for them to appreciate it as a normal distribution, right? In theory, for fun, like with rainbow trout, just still haven't tried, right? We can take 30 and just be like, cool, right? So that's that. So real quick, let me just recap. I know a lot was said real quick. Let's just do a little quick recap. So what does the central limit tell us, right? The central limit theorem gives us information about the characteristics of the x bar sampling distribution based on all samples of size n. When n is sufficiently large, meaning greater than 30, right? Greater than or equal to 30 in most cases, the central limit theorem tells us that the x bar distribution is approximately normal. The mean of the x bar distribution is mu, right? The mean of the original x distribution and the standard deviation, also known as the standard error of the x bar distribution, is sigma divided by the square root of n, where sigma is the standard deviation of the x bar of the x distribution. Excuse me. Just to recap real quick. It's more so for your homework. I know y'all probably done with the homework already. I'm sorry about that. All right. So let's summarize this information for convenient reference. For almost all x distributions, if we use a random sample of size 30 or larger, the x bar distribution will be approximately normal. The larger the sample size becomes, the closer the x bar distribution gets to the normal, right? So furthermore, we may convert the x bar distribution to a standard normal distribution using the following formulas, right? And we're going to recap again. All right, so using the central limit theorem to convert the x bar distribution to the standard normal distribution. All right, once again, the mean of the x bar is going to be equal to mu. The standard deviation of the x bar distribution is equal to sigma, the standard deviation divided by the square root of n. We can use this formula here. Z is equal to x bar minus mu over the standard deviation over the square root of n, right? And this is where we have n is a sample size of 30 or better, right? Mu is the mean of the x bar distribution, and sigma is the standard deviation of the x bar distribution. All right. Let's go through an example real quick. And like the previous example, this is the one that's like your homework. So a certain strain of bacteria occurs in all raw milk. Yuck. Let X be the bacteria count per milliliter of milk, right? The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound-shaped and symmetrical. The mean of the X distribution is mu is equal to 2,500. That's a count, right, of the bacteria. And the standard deviation is sigma is equal to 300 in a large commercial dairy. Dairy. How you say that? Dairy. Right? The health inspector takes 42 random samples of milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria count X bar, right? So we want to figure out how much bacteria is in this milk, right? Apparently some bacteria is enough to consume. They wonder why we'd be taking antibiotics, whatever. So assuming the milk is not contaminated, what is the distribution of the X bar, right? Of the sample mean. Let's take a look. So the sample size is n is equal to 42. Since this value exceeds 30, the central limit theorem applies. And we know that X bar will be approximately normal with the mean mu is equal to 2,500, right? Mu of X bar, excuse me. And sigma of X bar is going to be equal to the standard deviation sigma divided by the square root of n, or the 300, which we're given, divided by the square root of 42, each one of those samples, right? That's going to turn out to be 46.3, right? 46.3. All right. So now, assuming that the milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between 2,350 and 2,650 bacteria per milliliter? Jesus, that's a lot. Milliliter is like a drop, like. A lot of bacteria. All right. Y'all gonna learn about this in Bio 28 when y'all take it, you know.
28.
Bio 28, yep. Yeah. So we convert the interval 2,350 less than or equal to X bar less than or equal to 2,650 to a corresponding interval on the standard z-axis. So we're using the formula. Z is equal to X bar minus mu over the standard deviation divided by the square root of n. Just plug in the numbers right there, right? So we're going to have 2,350 minus 2,500 over the 46.3. And we're going to have the 2,650 minus 2,500 over the 46.3, which is going to give us two z values, negative 3.24, positive 3.24, right? So what do I want to know? I want to know what's the probability in between those two z values, right? Again, calculator, chart, whatever, you know. I prefer the calculator though. And then it gives us this. So the probability of X bar being between 2,350 and 2,650 is equal to the probability of Z being between negative 3.24 and 3.24, When you do it in the calculator, you get 0.9988. So the probability is 0.9988 that X bar is between 2,350 and 2,650. That probability is way too high. Way too high. I'm just saying almond milk. That's all I'm saying. Cashew milk, rice milk, oat milk. Just saying. Coconut milk. Just saying. All right. Interpretation, right? So at the end of the day, right, the inspector must decide to accept or reject the accumulated milk that has been held in cold storage awaiting shipment. Suppose the 42 samples taken by the inspector have a mean bacteria count X bar that is not between 2,350 and 2,650, right? If you were the inspector, what would be your comment on this situation? So we have two situations, right? What if the bacteria is less than the 2,350? And what if the bacteria is more than the 2,650? What would you do, right? So here's how the decision is made. I'll show y'all. There's some good stuff right here, good stuff. Basically, in between that probability, those two numbers of 2,350 and 2,650, that's the safe to consume range. Think of it like that. What happens when it falls out of it? So the probability that X bar is between 2,350 and 2,650 for the milk that is not contaminated is very high. If the inspector finds that the average bacteria count for the 42 samples is not between the 2,350 and 2,650, then it is reasonable to conclude that there is something wrong with the milk. If X bar is less than 2,350, you might suspect someone added chemicals to the milk, right, to artificially reduce the bacteria count, right? That's them antibiotics right there, right? If the X bar is above 2,650, you might suspect some other kind of biological contamination, right? I blame the bats. I blame the bats, you know? I mean, y'all lived through COVID. Y'all already know. I ain't saying nothing new. So let's look at the procedure. How do we calculate this, right? I'm gonna give y'all the recipe right now. So how to find probabilities regarding the X bar, right? The sample mean. So given a probability distribution of X values, right? So this is what the questions are going to be giving you, right? You're going to be given an N, a sample size. You're going to be given a mean of the X bar distribution, and you're going to be given a standard deviation, right, of the X distribution. If the X distribution is normal, then the X bar distribution is normal, period, right? Even if the X distribution is not normal, if the sample size for N is greater than or equal to 30, then by the central limit theorem, the X bar distribution is approximately normal, right? So what you're going to do is convert the X bar to Z using the formula, right? X bar minus mu over the standard deviation sigma divided by the square root of N, and then use a standard normal distribution to find the corresponding probabilities of the events regarding the X bar, the sample mean, all right? So basically, you're doing the same thing you did last week with a brand new formula. That's it. All right. Let's talk some more about this now. Y'all know I need to nerd out for a little bit. All right. So we're going to talk about biases and variability. So whenever we use sample statistics as an estimate of a population parameter, we need to consider both biases and variability of the statistic, right?
This is the part where we take out the highest value and the lowest value somewhere?
Can be. That could be one way to fix it, right? So a sample statistic, right, is unbiased if the mean of its sampling distribution equals the value of the parameter being estimated, right? That was deep. Let me say that again, right? A sample statistic is unbiased if the mean of its sampling distribution equals the value of the parameter being estimated, all right? That's some good stuff right there. So you can't talk about means and not talk about spreads, right? So the spread of the sampling distribution indicates the variability of the statistic. The spread is affected by the sampling method and the sample size. Statistics from larger random samples have spreads that are smaller, right? So larger the sample, right, the smaller the spread, right? So it's more like, up, so to speak. All right. So we see from the central limit theorem that the sample mean X bar is an unbiased estimator of the mean mu when n is greater than or equal to 30. The variability of X bar decreases as the sample size increases, right? So more samples, right? Less variability, more upright, right? So in the next section, we will see the same proportion p hat is an unbiased estimator of the population proportion of success p in binomial experiments with sufficiently large numbers of and trials. Again, we will see that the variability of p hat decreases with increasing numbers of trials. The sample variance S squared is an unbiased estimator of the population variance sigma squared. All right. And that's it. Good stuff to know, good stuff to know. Is there any questions about it?
That's a lot of information.
It is.
It's a lot of information.
I got you. Good.
Need to see some practice problems online.
Why?
We just did two.
Why?
Why we do this? So that we can calculate the likelihood that something will occur.
Yeah.
Right.
So
We're doing this so that we could go to Vegas and make money. Right.
yeah.
So we end in gambling in our life.
That's it, this is the class.
Yep, that's it.
Could we do,
Yeah,
do us
yeah.
one big favor, could we do at least the homework?
Sure.
Like, could you do it, like, on the board?
Do it. It's the same thing.
No, like,
Yeah.
obviously, we're gonna do it, but let's do a practice one.
All right, we can do that.
Like, you're gonna give random numbers?
Pretty much. I mean, your homework doesn't even have a story.
Yes, it is, it's like the normal population of who, given a normal population whose mean is 635 and whose.
Yeah, but that's not a story.
Yeah, it's not like rainbow trout.
Yeah. So look, long story short, right? You're gonna have a homework question, right? It's gonna say like, I'm just really summing this up. They're gonna ask you like, oh, what's the probability that X bar, right, is less than 15, right? Making this up off the top of my head, right? In addition to that, you're gonna be given a sample size. Let's say that my n is equal to 35, making this up, right? Let's say that my mean mu X bar, whoops, there we go. Let's say that is, I don't know, give me a number. 9.
It's too low.
It's fine. And then let's say that my standard deviation sigma is equal to 23. Right?
Okay, wait. Slow down.
All right. I'm just making this up.
Savannah.
I'm just making this up, right? So long story short, we want to know what's the probability of X bar less than 15. So what am I going to do? I'm going to convert that into a Z value. That way I can actually do it in my calculator.
We're gonna subtract 35.
15
No.
from
15 from 35?
so
No, from the mean.
so here's what we're gonna do. We're gonna change the X bar to Z. We're gonna use this formula: X bar minus mu over sigma over the square root of n. This is all in your formula sheet, just copying it from there, right? After that, you're just gonna plug in the numbers. So this is gonna become probability of Z less than, what's my X bar? 15 minus my mu, which is 9.
Divided by 35? No, 23?
23 divided by the square root of n, which is 35. And that's it. Right?
I mean,
Calculator. Yeah. So I'm gonna have probability of Z is less than, I'm gonna cheat because I don't even know what this is. I'm making this up on top of my head. So what's this? 15 minus 9 divided by standard deviation, which is 23, divided by the square root of 35. Let's call it at that. So I have 1.543325. That's what I got, right? Those of you using the table, right? You could kind of round this off to probability of Z less than 1.54. Everybody else using the calculator, you know what to do, right? So when we type this in the calculator, let me see what I'm gonna get. Let's see. So I get my answer 0.938624. And that's it. That's your whole homework. Well, if it's greater than, you do 1 minus that. If it's in between, you know, lower bound, upper bound, enter, boom, that's the answer. That's it.
They put that answer in the calculator.
I'm still.
Huh?
How do you plug that into the calculator?
So when you go into the calculator, right? Should have grabbed that. Give me 1 second real quick to get a. Yeah, that is a sample.
No, like on the
board. Yeah. Hold on 1 second. Let me just get the 6. Give me 1 second real quick. I'm just trying to get the keyboard. That's what I want. Keyboard.
You're recording the class, right?
Yeah. This part I'm recording as well. Open. My fault. I'm just trying to get the keyboard real quick. Just give me 1 second. Got y'all. Bless you, whoever that is. Right, sorry about this. Gotta stop sharing for 1 second. So that I can show you guys this. There you go. Well, let me just. Put this. I'm telling you, that power outage made this better because this is a lot clearer than what it used to be.
You're gonna show how to do it on the calculator?
Yeah, I'm gonna do that real quick right now. So I'm just getting my red pen. Right? So if I was gonna do that problem that we just did, first thing I gotta do, I gotta go to second, right? Then you're gonna go to stat regression / distribution. That's the data button right here.
Right.
Right? Then what you want to do is you want to go across. Right? So second data. Then you want to press the arrow to go across to the right, I'm talking about, right?
Yeah.
And then you want to go down. So where it says, right, binomial PDF. No, CDF. Sorry, yeah, CDF. Sorry about that, right? Wait, hold on.
Isn't it the
Normal.
normal
right.
CDF?
I forgot the question that we're doing. Normal CDF. There you go, right? So when you press enter, if I'm not mistaken, they're gonna ask you for a mean and then a standard deviation, right?
Yep.
Ask you for the mean and standard deviation. So for a normal distribution, what is your mean and what is your standard deviation?
1 and 0.
Right, so mean is 0. Standard deviation is 1.
Always, right?
Right. Then they're gonna ask you, right, for a lower bound
And for
and an upper bound, right?
You're gonna go back to school, right, before this.
Yeah. So in our question here, right, we have z is less than 1.543325. So that means that I'm gonna be doing a distribution like so. All right. So let's call this 0. And my number is 1.54, just rounding it off. Let's just say that 1.54 is right here. And let's call that z, right? I want to know the area here to the left of this, right? So what do I want to know? I want to know from negative infinity up to 1.4. So my lower bounds, right, is negative infinity, which remember in the calculator is what? Negative 1e 99. That's already there, so you don't have to worry about typing that in. Negative 1e 99. If you accidentally erased it and you wanted to get the e back, right? Let me show you where that e is real quick. That's
Isn't
right
that
here.
the second 5?
No, just plain old e right here by itself. Right?
Just pressing the E.
Yeah,
and
that's the EE that's there, right? Like in between the E99. The upper bound,
it will be
1.54.
1.54. Give you the answer.
And enter, and then boom, you get the 0.938624.
So that would be
That's
the
it.
last step of after you find the Z.
Right.
Okay.
If it was greater than, right, your lower bound would actually be the number, the Z value, and your upper bound would be infinity. So 1E99, right? And that's for greater than. For in between, your lower bound is a smaller number, your upper bound is a bigger number. That's it.
And if it's negative, it's your lower is negative, and then
That's possible. It can be negative, it can be positive.
just stay with it, not vice
Yeah.
versa. That's how it's normal.
And that's it.
Thank you, Professor.
You're welcome. I'm gonna stop the recording now, okay?
Yeah.
All right, so everybody online, have a great week. Remember pantry this week. Happy belated Halloween. You guys can still do test corrections if you haven't done so already. All right, the lab will be open today from 12 to 6. Lab will be open next week, Monday through Thursday, 10 a.m. to 11 a.m. Sorry, to 8 p.m. and Friday and Saturday from 12 p.m. to 6 p.m. All right, see you guys next week. Have a great weekend and a great week. See you.